All right, 659, Glencoe Matter and Change Chemistry Textbook, Neutralization. So you have your should have your notes in front of you there with some blanks here. I'm going to fill in the blanks for you as we go through. Neutralization. Well, we know about different types of reactions. Neutralization, acid-base neutralization is one of those types of reactions that we studied in Physical Science 20, along with, synthesis and decomposition and combustion and all the rest of it, right? Single, double replacement, so on. And so when we're talking about neutralizing, we just talked about pH. We just talked about acids, and we're talking about acids and bases. So when you have an equal number of moles of strong acid and an equal number of moles of a strong base, then those should neutralize each other. So think about it. If the pH of one is 13 and the pH of the other one is 14, and you mix those together, that should be a pH of 7, right? They kind of counteract each other and so on. So neutralization is something very important when we talk about acids and bases. When acids and bases react, you should know this from our previous course, they form an ionic salt and water. So acid plus base forms a salt and a water. So if we have, let's say, an acid HCl, very strong acid as we know, and we're going to combine that with sodium hydroxide, let's say, very strong acid as you know, those would be aqueous, both of them, dissolved in water solution. And what's going to happen when those react, the hydrogen, as you know, is going to donate its proton. So it's going to get rid of the H, and that H is actually going to connect with the OH to make water. So it's like it's a special double replacement reaction, right? So the H is going to go with the OH to make H2O, and guess what? The sodium is going to kind of go with the Cl to make sodium chloride. Now, it does so happen that obviously liquid water here, and this is aqueous salt. It would be dissolved in solution. But nonetheless, the pattern for the neutralization reaction is acid plus base equals salt and water. Okay? And this salt comes from the anion of the acid and the cation of the base. That's where it comes from. So typically, there are no reactants left after a neutralization reaction. Acid and base have been completely neutralized, and the pH is 7. So it's basically a perfectly balanced solution. So a strong acid, as you know, would fully dissociate, and a strong base would fully dissociate. So we just have water and salt, none of which would produce any significant hydrogen ions or hydroxide ions to make the solution basic or acidic. Now, that's not the case in every single neutralization reaction. Sometimes the pH creeps up a little bit when we have strong acids and weak bases, and vice versa, because there are some unreacted things in there. But for strong acids and strong bases, we can assume that we're going to have a pH of 7 when it's all done. And I guess that's what I said here. In some cases, salt products react with water to produce acidic or basic solutions, but we'll focus on this as just neutralization. All right. Okay, so if you look at your textbook there, the textbook has, and I don't have the picture up on the screen for you, but the textbook has pictures of different commercial antacids, okay? So there are things like Tums, okay? You know about Tums, maybe you've heard of those. Rolaids, I think Rolaids? It's what? Rolaids. Rolaids? Okay. Let me finish here. Yeah, milk of magnesia. That's another one. It's maybe a little less common. And what did you say? Pepto-Bismol? Yeah, I suppose Pepto. Sure, Pepto. Let's say. So these would be products that you would medications. Let's say they're antacids is what they're called, and they basically their job is to neutralize the excessive acidity that would be in your stomach. So I mentioned the other day, if you have heartburn or if you have an upset stomach. Sometimes it's because of the heartburn is because of acid reflux. So the gastric juices in your stomach, for whatever reason, there's your acids are kind of like working their way up into your tract up there, your upper tract, and it's kind of getting to where it's not supposed to be. The stomach is well lined and protected, and the food goes down to your stomach. The acid acts on it, dissolves it, so your body can take its nutrients and use it. But if that acid starts to creep up, you get this heartburn and it's uncomfortable. So what happens is you take some Tums or Rolaids or whatever these things are, and it's supposed to neutralize the excessive acid sort of action in your stomach. It's supposed to calm things down a little bit. So it neutralizes your stomach acid to a certain degree. Now, we may do a lab with these things here, and we may actually assess these things. Maybe that's kind of a plan for this year, but anyways, we can actually determine how effective these might be by putting them into an acid solution and finding out how it changes the pH and that sort of thing. So that's what neutralization is. That's how it's used to help us. Okay, titration. We need to talk about titrations here. This is sort of the way that chemists can actually determine how much acid, how much base is in a solution, the pH of a solution. And titration is a method, and we're going to, again, I'm planning to do a titration lab with you here coming up. But this is a method by which we can determine with a lot of precision, how much acid or what the concentration of an unknown acid solution would be or a basic solution would be. So how do titrations work? In order to find an unknown concentration of an acid or base, one would use this titration method. A simple titration may involve the presence of an indicator. We haven't talked a whole lot about indicators, but indicators would be either weak acids or bases that actually have a color change at a certain pH. And I'm not sure if this is in your textbook or if I just grabbed this from Mr. WWW. But anyways, this is a listing and kind of a graphic display of different indicators, okay? So the indicator's color would tell you, yes, we're British, okay. It would tell you the pH of the solution. And so when the solution gets to a certain pH, it would trigger a color change in the indicator, thus indicating that you've hit a certain pH. If the indicator turned color around pH 7, then a visual indication of the equivalence point would be seen. So equivalence point is something new that you haven't heard of before as well. The equivalence point would be where you would have the same number of moles of acid as you would of the base, or of the hydronium ions and the hydroxide ions. So it's where they're equal, and that would be at pH 7. That's slightly different than the endpoints of a titration, which you're going to read about. We may talk about a little bit later. But so let's just take a look at this graph here then. And what would happen is, let's say we have some kind of acidic solution, and the pH is right here at about pH 2, very, very acidic, okay? And so if we add base to this acidic solution, the pH is going to crawl up here, creep up, okay? And so look at what happens when the pH is 2, and we have an indicator. Let's say we have a few drops of thymol blue in this solution. Well, at pH 2, that solution will be colored red. At pH 3 or so, right here, and again, maybe I'll need to zoom in so you can see that at the back. But at pH 3, this indicator will change color. It will go from red to yellow right about here. So as soon as that color change happens, you kind of have an idea the pH of the solution. So if you wanted to end your titration at pH 3, the end point, pH 3, then you might use an indicator of thymol blue, because it's going to be red, you're going to add NaOH, add base, whatever, blah, 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 and then boom, we have a color change. You stop, and you know what pH is. You can then do some calculations. How much base did you put in? And you can kind of go from there, and that would have counteracted, or that would have brought the pH from, up to at least 3. So, okay, so let's keep going. Let's say, let's see, the one we have in the lab that we're going to use is bromothymol blue, okay? Bromothymol blue. So let's say we have a real acidic solution. We keep moving this bar up here. Bromothymol blue, it's clear, maybe a little yellowish tinge, okay? Pretty clear here. We move up, move up, move up. When we hit this point right about here, it starts changing color. Oh, wow. And at this point here, there's a solid blue that should come about. So guess what? In between this first color change and the color change of blue, This could be only a few drops of strong base that would cause this color change. But if you were able to stop where this is changing color from yellow to blue, right in the sweet spot here, guess what? That's pretty much what? 7. So a completely neutral solution. And again, it's not an exact science, but with the indicators, that's what you do. You say it's yellow here, it's blue here, so right in between, this sweet spot right here, that's going to be pretty much pH 7. So that's the indicator that we have in the lab and that we might be using for an upcoming lab. But it's as simple as that. Now, if you had a very basic solution, okay? If you had a very basic solution, let's say pH is 11, it starts here, then your bromothymol blue is probably going to be blue here. It's going to be blue. And then as you work down by adding acid, it's going to go from blue, change color to, green, then boom, yellow. So right at that sweet spot there, again, pH 7. So it's going to go from blue to yellow, or from yellow to blue. Right? So the end point of a titration, the end point would be where your indicator makes its definite change, and you know what the pH is going to be then. So for thymol blue, let's say, different than bromothymol blue, thymol blue, okay, it's going to be red at very acidic ends. In here, from 3 to about 8, it's going to be pretty yellow. And then it's going to turn a solid blue between 8 and 9. So the end point here, if you're looking for this creation of the blue, if the solution turns blue, that end point will give you a pH of 9. You can bet that that's a pH of 9. Any questions about indicators there? Yep. Is that how the drug tests work? A little bit more complicated than that, I think. They're not just looking for pH, they would be looking for presence of other chemicals. But yes, it's an indicator solution. So yeah, so you see on border security or something like that, right? They take a swab of someone's luggage that's and they put it in this little baggie who has this little solution, and they shake it up, and if it turns a certain color, you know there's a presence of a certain chemical. So yeah, same idea. Wouldn't be these indicators just for pH. They would be a little more complicated than that. But yeah, there would be chemical means by which they would determine what chemicals would be in the solution. Yeah, same idea. Good. Any other questions? All right. Okay. Now, using an indicator is one thing. You could also use pH indicating technology, and if you had a pH instrument, and it was able to plot on the computer what the pH is at a certain time or a certain volume added, so you would be adding base, then all of a sudden, boom, there's a big wild change in pH. Well, at that point, at this volume right here, would be the volume of NaOH that you would need to add to counteract to completely neutralize, pH 7, completely neutralize the acid that's in there. So if you have let's say this is your solution, if you have a lot of acid in there, you're going to need a lot of base to neutralize it, right? If you have a very small amount of acid in there, so let's just say compared to the solution, this is the actual acid, then you're going to need a small amount of base to actually counteract that, right? So the volume of NaOH added, if it's a lot of NaOH you have to add, that means there was a lot of acid in there to begin with. And so in a titration, in a lab, in an activity like that, you would take the volume with the known concentration of your NaOH, and you would be able to find how many moles you actually put into the solution. And that would have to be the same number of moles of a strong acid that would be present in there before. So if you find the number of moles that you added, you can assume that there would be the same number of moles that were actually in there. So you could determine the concentration of the acid that was there at the beginning. Okay, titration. So as we just kind of continue this exploration here, this explanation, if we knew the concentration of the standard solution, so let's say, as I described, the NaOH that we put in was basic, then the unknown concentration of the acid could be determined when the acid and base are completely neutralized. At this point, the pH is 7. and the concentration of OH minus NH3O plus is equal. So you have a standard solution of known concentration, and then you have another solution of unknown concentration. And when they're completely neutralized, you can determine from the standard solution exactly how many moles of, in this case, the base that you added. And it should be the same number of moles of acid that was in there to bring it to pH of 7. Now, in order to titrate, and I might just show you a little demo here a little bit later in the class. And like I say, I am planning a titration lab for you guys this year. So you'll be able to do this on your own, but I'll show you how it works in case we don't get to it. To titrate, one slowly adds the base to the acid solution, or vice versa. But if you start with an acid, you would add the base. The end point of the titration is reached when your indicator, in this case our bromothymol blue, would indicate that we have a pH of 7. That's when we stop, the end of the titration. It's also the equivalence point there too. You then measure exactly how much base solution you added to the acid. Find the number of moles of the base, and that's of course volume times the concentration, the molarity. Use the balanced neutralization equation to determine the molar ratio of acid to base. Usually it's a 1-to-1. Divide the number of moles of acid by the volume of the new solution, and you have the concentration of the acid. If the neutralization equation is a 1-to-1 ratio of acid to base, then the convenient, this is a convenient ratio here, C1V1 equals C2V2. So if you have a concentration times a volume and those moles need to be equal to another concentration, well, you can simply find the other volume. Concentration of the one times the volume should equal the concentration of the second one times the volume. So you can solve for any unknown in this ratio. C1V1 equals C2V2. Multiplying concentrations by volume always gives you moles. All right, I know that's a lot of just words and explanation. You might want to read that over a few times, and once you actually kind of have a little bit more experience with doing some questions, possibly some titration in the lab, it'll maybe make a little bit more sense to you. But let's go over this problem here and work through this. This one's in your textbook, a sample problem, and let's see, it's on problem 6. Yeah, 660. Oh, I have it up there. 664. There we go. There we go. Okay, so molarity from titration data. Okay, so this is a sample titration, and we're going to use the data that was determined here to do some solve some stuff here. So, a volume of 18.28 milliliters of standard solution of 0.1 molar NaOH was required to neutralize 25 milliliters of a solution of methanoic acid. Okay, HCOOH. What is the molarity of the methanoic acid solution? Okay, so what's the molarity? So again, we have a volume and a concentration that's known. I have a volume, and I'm trying to find an unknown concentration. Okay? So let's just read the first part of here. You're given the molarity and volume of NaOH and the volume of methanoic acid. The volume of base used is about 4/5 the volume of the acid, so the molarity of the acid should be less than 0.1. Now, I think that in the textbook, they don't use the C1V1, which I like a lot. I think it's a little bit more complicated, their solution. So I'm just going to show you that C1V1. It's pretty straightforward. Now, technically, to get moles, you would multiply moles per liter times liters, right? That gives us moles. And so if we're going to have moles per liter over here, we should multiply by liters as well. As it stands, guys, if this volume, as long as these volumes are the same units on both sides, it actually really doesn't matter if you change this to liters or not. But just to be consistent, so I'm not, making anything really silly here, I'm going to show you, we're going to convert to moles. So the concentration, let's say we have NaOH, okay, over here. And we have methanoic acid over here. And so NaOH, 25 mils. So we divide by 1,000 to get volume of 0.025 liters. The concentration of the base is 0.1 molar, with some more sig figs there, obviously. All right, what do we know about the acid? We know the volume of the acid is, what was it, 25 as well? What? Oh, my bad. This is actually the volume of the base. This is 0.018. Okay, this one. Base. And this one is 0.025. There we go. And concentration we don't know. So C1V1 equals C2V2. If we're trying to make the same number of moles, then we simply do this. 0.1 C1 times V1 equals C2, concentration of, let's make that the acid, Ca, V2, 0.025. So we divide both sides by 0.025. And we get the concentration of acid. Okay, so we have 0.1 times 0.018 divided by 0.025. So it looks like 0.072. 0.072, and that's going to be in what? Remember, this is concentration, so concentration's in moles per liter, capital M. Okay, so for complete neutralization, strong acid, strong base, or acid base, I guess you don't have to assess whether it's really strong or weak. You want the same number of moles. Obviously, if something's stronger, it's going to take a little bit less to neutralize it. Questions there? Pretty easy? Okay. All right, so 664, there's some questions for you to work on here right now. So why don't you take a few moments and work on those questions from the textbook through the year. All right, so so students, for number 44, right? Number 44, you actually don't have to change the milliliters to liters. You'll get the same answer if you just leave them as milliliters, as long as they're both milliliters. So you can change them, divide by 1,000 for each of those volumes, make them liters, but you can just write it as milliliters as well. You should get the same answer. So your answer should be 0.2167 or something like that, 0.22. There are there's 4 sig figs is what you should write it to, so 0.2167 should be your final answer there. That's for 44. Okay, so I'm just going to go over all 3 questions here real quick with you. So 44, now the C1V1 equals C2V2 works real well if it's a 1-to-1, okay? Works real well. You don't have to go through all of this. This is a little extra. This is finding out exactly how many moles you have and then using the molar ratio and then finding out the volume or concentration, whatever. So C1V1 equals C2V2 works real well with 1-to-1 ratios. I mentioned number 44 already. 45 also is a 1-to-1 ratio here. Okay? So C1V1 equals C2V2 works real well as well here. You notice this 1-to-1 ratio here. Now, where we get into a little bit of a problem with C1V1 equals C2V2 is when we have not a 1-to-1 ratio. So watch this. In number 46, the reason why this is a bit of a challenge is because this is a 3 NaOH to 1 H3PO4. So when it's a 3-to-1, what that means is that in order for this to react, 3 moles of NaOH reacts with 1 mole of H3PO4. That means in order for H3PO4 to neutralize all of the NaOH that's involved here, you need actually 3 times as much of the smaller one to be equal. So you don't multiply the NaOH side by 3, but you multiply the acid side here by 3. Okay? So C1V1 equals C2V2 still works, but when you have a 3-to-1 ratio like this, you have to multiply the one that's lower in ratio, you have to multiply that up so that it's equal. So that's why the C1V1 equals C2V2 still works, but you have to multiply by 3 here, because there's 3 times as much acid that is going to be required to equal the amount of base that's involved. Okay? So it still works. I still like this method. But again, if you just do the mole method, then this 3-to-1 takes care of itself up here. But I still like this method, but you just have to know if it's a 1-to-1 or something else to 1. And you should get 15 milliliters. Again, you do not have to convert the milliliters to liters if you use milliliters on both sides. Okay, so milliliters on both sides. So there's your 44 through 46. Any questions about what you see up there?